Welcome, geology students. This is video introduction number 2 for the second set of questions on the groundwater lab. These are questions 2E, 3C parts 1 and 2, and 3C part 3. Okay, for the first part, question 2E, we're going to be referencing this topographic map right here of the Mammoth Cave area in Kentucky. And specifically, we're going to look down here at this southeast corner of it. I'm going to zoom in a bit on that particular part of the map, try to anyway, and so we're looking right here at this particular part of the map. And question 2E reads, in what direction does Gardner Creek flow and what happens to it? So here's Gardner Creek, and so the question is, which way does it flow? So remember what your contour lines do when they cross a stream channel, and that will help you. And then what happens to it. And so you'll have to read some of the introduction to this to maybe figure that out, or apply some knowledge that you got from another portion of this lab to answer that second question. Okay, the next set of questions then revolve around this map right here. I think somewhere on it, I think I might have labeled figure 910. It's actually from a previous lab manual. This is the correct map, so don't worry about that. Okay, so we're looking again at the Mammoth Cave area in Kentucky, but now we're looking at groundwater information. You'll see green lines on here. They look like contour lines. Of course, they're not brown, but they're actually water table lines. And so here, this is at 700 feet. You'd go down the ground to 700 feet below above sea level. Here 600, here 500. And like on the surface, groundwater flows downhill. And so the flow would be along this direction here. Notice the flow lines all turn. And so to indicate which way groundwater would flow, to help us visualize it maybe a little bit better, there are these red lines on there. These red lines, and you notice there's an arrow on the end of them, take into account these green lines and tell us which way the groundwater is flowing beneath our feet in this part of Kentucky. So question 3C talks about a creek which disappears at point X on the map. Okay, disappears, you ask. What does that look like? Well, there are actually streams in this part of the country that look like this, that do this. Here's a stream that's just flat out disappearing. Now, of course, the ground here is very porous, and it's disappearing underground through cracks and crevices, and entering a cave system under the ground somewhere in this area. That's where it's going. But from the surface, it does look like it's disappearing, and it's kind of a neat look. So that's a disappearing stream. And then you might also remember from our trip to Sojan, Wang's area, to get fossils. There was a barn right here. We stopped. This was our last stop, and I pointed out down in this little valley. I said, look right here, because this is an artesian well. So right here, water is actually coming right out of the ground. It does not have to be pumped, and so here is an example of a spring. In this case, you can see the stream actually starts here and goes down, and that's because this layer of rock here has water in it. It's being pushed on by the overlying layers and pushes that water out. So this would be a spring, and this would be a disappearing stream. So those would be terms that would be used in this question. And so right here, it says there's a creek that's disappearing, like I just showed you, and dye was placed in the water here at this particular X marks the spot. And of course, it would then flow down these red lines in that direction. Okay, and so it says predict where the dye would reappear at the surface and mark those points on the map. And so you'll have a map that you actually need to write on and show me where that dye would reappear at the surface. Now I want to point you to this legend here, and notice this. Here is a perennial spring, like we saw at Wang's and Sojan. On a topographic map, this blue dot indicates where those occur. This line with a triangle at the end of it is where a disappearing stream sinks underground. And so, for instance, on your map, right here, there's a spring that pops up to the surface. It flows just a little ways, and then the triangle tells us it disappears underground. Here also, the round blue dot is a spring. Water comes to the surface, flows a short distance, and then at the triangle, disappears underground. Okay, so you're supposed to then predict where the dye would reappear at the surface and mark those spots as it says in part 1. Part 2, so part 3, see part 2. What is a hydraulic gradient in feet per mile? Don't be bothered by the term hydraulic gradient. That's basically just the slope down which the groundwater flows. Okay, you can see that, and just like with surface contours, the closer together the contour lines, the steeper the slope. The farther apart the contour lines, the more gradual the slope. And so it says, it asks you to determine the hydraulic gradient between this point right here, X marks a spot, and I'll give something away. This point right here, which is the first spot that the dye would have a chance of popping back up to the surface. You see that blue dot? That tells you that's a spring. Here's the course down which groundwater flows, and it would pop up to the surface there. So what's the gradient? Well, you'll notice here there's a green line here and there's another here. This one's darker. So if we go down here, we'll see this is the 600-foot contour line for the groundwater, not the surface, but the groundwater. Well, there's 20 feet of difference in contour interval here, right here. See that in the legend? 20 feet of difference. Well, if this is 600, this must be 580. Okay, so that's X is at 580. I'm giving you that. So then you'll go down here. Well, there's 500, and there's another line, there's another line, there's another. You'll notice it loops right back around, so it's going to be just a little bit less than whatever this line is right here. So the difference then between this line here and this spot here in water table elevation is your H. That's the height difference between the start where the dye was placed and this spot, which is the first place it could come out of the ground. Well, to determine L, take a piece of string and lay it along this surface, and then go over to the legend here and figure out how long that string is once you've straightened it out, and that will give you your L, your length over which the groundwater flows. Well, come on now, behave. Okay. So, if you then look here, you're going to have H over L, and then it says use the water level contours to measure and to show your calculations, but it wants your answer in feet per mile. So you may again have to convert miles to feet. Remember, there's 5,280 feet in a mile, and that should get you through question 3C2. Okay, here's the last one, 3C3. If dye took 152 hours to travel from X to this spot, so 152 hours, and remember, you've already determined that distance. What is the average velocity in feet per hour that basically the dye and the groundwater carrying it is flowing in this portion, underneath the ground in this portion of Kentucky? And again, an answer in feet per hour. Okay, so figure out how fast the groundwater is flowing here. And the last thing, I'm adding this onto this question. I want you to compare your answer from this question with your answer to question 1D from the Nebraska area. And I think you'll find it kind of interesting. I hope you do. Okay, thank you. Back with another one shortly.